2011, a faint star deep toward the galactic center brightened for 270 days, then faded. No object crossed in front of it that any telescope could see. Something massive, dark, and silent had drifted between that star and Earth. It would take two rival teams, 10 years, and a bitter disagreement to work out what. A rogue black hole is exactly what it sounds like. Not the kind anchored at a galaxy's core, and not one locked in a binary devouring a companion. This is a stellar mass black hole, wandering the galaxy alone, gravitationally bound to nothing. Most form when a massive star collapses and explodes as a supernova. If that explosion is even slightly lopsided, it kicks the newborn black hole like a rocket, hurling it out of its birth cluster at tens or hundreds of kilometers per second. Alone in empty space, it has nothing to feed on. No companion star, no swirling disk of superheated gas, no X-rays. It emits no light of its own by definition. A black hole with nothing falling into it is, for all practical purposes, perfectly invisible. Even that isn't quite absolute. A drifting black hole does sweep up thin interstellar gas, and that gas can glow faintly as it falls in. But the wisps between stars are so sparse that the glow is far too dim for any telescope to spot across thousands of light years. There is only one way to catch a truly isolated one, and it comes from Einstein. A black hole's gravity bends the space around it, so when it passes almost exactly in front of a background star, it acts as a lens, magnifying that star's light. Astronomer Bohdan Paczynski proposed using this effect in 1986 to hunt for dark, massive objects. When the alignment is close, the star brightens smoothly over weeks or months, then dims again. No color change, no flicker, just a clean, symmetric rise and fall. Two survey programs made the hunt practical. OGLE, the optical gravitational lensing experiment in Chile, and MOA in New Zealand. Every clear night, they photograph hundreds of millions of stars toward the galactic bulge, watching for any that suddenly begin to brighten. On one such night in 2011, both teams flagged the same event, OGLE 2011 BLG 0462. A star in Sagittarius was brightening, and this one refused to fade on schedule. The magnification dragged on far longer than a typical passing star or planet. Estimates suggest the Milky Way hides on the order of 100 million stellar mass black holes, most of them isolated and dark. If that number is right, they are everywhere around us, and yet before this event, not a single free-floating one had ever been confirmed. A long event means a heavy, slow lens. But duration alone can't reveal mass, because a light, nearby object and a heavy, distant one can mimic each other. To weigh this thing, astronomers needed something photometry couldn't give them, a precise position. That's where Kailash Sahu and his team at the Space Telescope Science Institute turned to Hubble. Over 6 years, they imaged the field 8 separate times, hunting for a subtler signature than brightening. A tiny shift in the background star's apparent position. This is astrometric microlensing. The lens doesn't just brighten the star, it drags its apparent position sideways by a hair, then lets it drift back. Hubble measured that wobble at under a millionth second, like watching a coin move a few inches on the moon. In 2022, Sahu's team published their answer. The wobble implied a compact object of about 7 solar masses, roughly 5,000 light-years away, moving at around 45 kilometers per second. Too heavy to be a neutron star. They called it the first isolated stellar black hole ever found. That mass mattered. When a stellar core collapses, if what remains is under about 2¼ solar masses, it can survive as a neutron star. a city-sized ball of packed neutrons. Above that limit, nothing stops the collapse. It becomes a black hole. 7 solar masses put it well beyond that threshold. A confirmed black hole, drifting alone, betrayed only by the light it bent. It was the detection astronomers had chased for decades, and almost immediately, another team challenged it. Casey Lamb and Jessica Liu at Berkeley reduced the very same Hubble data independently. Same photons, same telescope, same star. Their pipeline handled the crowded background and faint neighboring stars differently, and it produced a strikingly different answer. Their estimate for the object's mass landed between roughly 1.6 and 4.4 solar masses. At the low end, that isn't a black hole at all. It could be a neutron star. From identical measurements, the two groups had extracted 2 fundamentally different objects. The dispute came down to blending. The light of unrelated stars leaking into Hubble's measurement of the lensed star. How you model that faint contamination shifts the inferred wobble, and the wobble is everything. A fraction of a pixel separated a black hole from a neutron star. Sit with what that means. The most direct detection of a lone black hole came from watching a star twitch by less than a millionth of a degree. And even then, experts staring at identical data couldn't agree whether it was a black hole at all. One object, 10 years of Hubble time, 2 rival teams, and a decade of argument to nail down a single wandering black hole. At that rate, cataloging 100 million of them is hopeless, unless the search itself changes scale. That's the promise of NASA's Nancy Grace Roman Space Telescope, expected to launch by 2027. Its wide-field microlensing survey will monitor hundreds of millions of bulge stars continuously, and it's forecast to uncover dozens of isolated black holes and neutron stars by their bent starlight. Meanwhile, the Gaia mission took a different route, tracking stars that orbit something unseen. It found Gaia BH1 and BH2, dormant black holes in wide orbits, and in 2024, Gaia BH3, a 33 solar mass giant just 2,000 light-years away, the heaviest stellar black hole known in our galaxy. None of those Gaia black holes are truly rogue. Each still holds a companion star that gives it away. The genuinely solitary ones, with nothing orbiting them, remain the hardest quarry in the galaxy, findable only in those rare chance alignments. The story didn't end in a stalemate. By 2023, both groups reprocessed the full dataset together, adding later Hubble epochs. The estimates converge near 7 solar masses, above the neutron star limit. The consensus now? It is, after all, a genuine isolated black hole. Its motion tells its own story. Drifting at roughly 45 kilometers per second, faster than the stars around it, it carries the fingerprint of a violent birth, the asymmetric Supernova Kick that tore it loose and set it wandering ages ago. There may be a second, stranger population of rogue black holes, ones that never came from a star at all. Primordial black holes, if they exist, formed in the first fraction of a second after the Big Bang from dense knots in the early universe. If enough of them formed, they could account for some or all of dark matter, the invisible mass holding galaxies together. That points to an obvious test. If space is full of small black holes, they should occasionally microlens background stars, so astronomers went looking. The Macho, Eros, and Ogle surveys, and later Subaru's Hyper-Suprime Cam, scanning the Andromeda Galaxy, ruled out primordial black holes across huge mass ranges. Whatever dark matter is, it isn't mostly black holes, the mass of stars, or planets. Even the microwave background and the survival of ancient star clusters have been used to rule out heavier primordial black holes. Slice after slice of the mass range has been closed off over the past 2 decades, but one window stubbornly refuses to close. In the asteroid-mass range, objects 100 billion times lighter than the Sun, small enough to slip through every lensing test, primordial black holes could still, in principle, make up all of dark matter. Trillions could be streaming through the galaxy unseen. So this is where it stands. We live inside a galaxy salted with invisible black holes. Some the corpses of dead stars wandering alone. Others perhaps relics older than the first star. We've confirmed exactly one drifting solo, and even that took a fight. Every one we find by accident. By the way, it warps a distant star's light for a few weeks, or nudges its position by a hair. They don't announce themselves. They pass, bend the sky, and move on. So, how many are really out there? And could part of the universe's missing mass be nothing more than tiny black holes, too small for any lens to catch, drifting through the dark? Right now, no one can rule it out. Tell me which explanation you'd bet on in the comments. We'll find out for real when Roman turns its cameras on the bulge and starts counting the ones we've been missing.